All right, E1 reaction rate stuff. So what's going to be the faster E1 reaction? This alkyl chloride or the alkyl iodide with water as our base? Well, just like it's always been, better leaving group. It's going to be more stable on its own, so it's going to leave faster. What's the better leaving group? The leaving group that has a larger surface area to delocalize the negative charge. So I minus is lower on the periodic table than Cl minus, so it's a better leaving group. That means that this one is going to be faster. So essentially, better leaving group. I'm just going to write Lg, better leaving group reaction is faster. So same as SN1, SN2, E2, and also for E1. All right, what about this situation? So we have the same everything besides our solvent. So we have water here, DMSO here. What's going to be faster, that one or that one? All right, good job. You've identified that this is an aprotic solvent. This is a protic solvent. DMSO is an aprotic solvent. Again, what are aprotic solvents? Solvents that don't have acidic hydrogens. So DMSO, acetone, dimethylformamide, DMF, those are all aprotic solvents. So how do these impact reaction rate of E1? Well, in general, protic solvents increase unimolecular reaction rates. So we would say SN1/E1 reaction rates. Aprotic solvents increase SN2, E2 reaction rates. So what's going to be faster? This one here, because we have the protic solvent. Right, we talked about E1 reaction rate a little bit, and now I have this next statement. So we have this thing up here, predict the product with water mixed with this alkyl halide, and it says, what the heck? Last chapter we learned that the reaction below, which is actually above here, would undergo a blank reaction. What gives? And essentially last chapter we would have said, so last chapter was all about substitution, we would have said, oh, we have a tertiary alkyl halide that's too sterically hindered to do SN2 chemistry. The nucleophile can't approach there. And also we have a weak nucleophile. That's not going to be that effective either. And because of that, we actually have to get the leaving group to leave before the nucleophile/base will do anything. And last chapter alone, we would have said, oh, okay, well, that'll ionize, that'll form our carbocation, and then the water molecule will add to that carbocation in an SN1 reaction. So that blank there, what the heck? Last chapter, we learned that the reaction below would undergo an SN1 reaction. What gives? The reality is that when SN1 happens, E1 also happens. So there's not a good way to force one of the reactions and not the other. So it actually turns out that if we had these reaction conditions, we're not going to have one major high-yielding product. We're going to get a mixture of the SN1 product plus the E1 product. So this is the SN1 product, this is the E1 product. So essentially, SN1, E1 reactions, as synthetic chemists, we want reactions that make something in a good yield. But because product mixtures result with SN1 and E1, these reactions, SN1 and E1 reactions, are not very useful. We still have to know what causes them to happen so that we can not have them happen if we can work that out. But essentially, any time that the conditions that we look at says that SN1 or E1 is going to happen, they're both going to happen. So now's the part in the chapter where we're really going to transition from just talking about elimination chemistry to discussing, we've learned about substitution, SN1 and SN2. We've learned about elimination, E1 and E2. Now, here's a set of conditions. What is it going to do? SN1, SN2, E1 or E2, or some mixture of those things. And depending on all the factors, the nucleophile, the type of leaving group, all of those things, it's going to be, all those things together will allow us to decide what reaction pathway is going to be the predominant one.